Hi everyone. So now let's talk about rasterization, right? So we already um, discussed a little bit of this. So we know that rasterization stage basically needs to generate the fragments for each triangle and also assign or compute the interpolated values from those portions of those triangles, right? So the first step we need to do with this rasterization stage is basically to compute the number of pixels or which pixels belong to each triangle, right? And basically what we are doing here is we need to convert information that is basically in a continuous mode, right? Because a triangle is a continuous object, right? And we need to convert this continuous information into discrete information, which is basically these pixels on the image plane. And so having a triangle like this, right, and in an image like this, and in this case is I think it's 18 by 18 pixels. This is obviously very small, but in reality, right, we have 4K images or monitors that obviously, yeah, we need to usually compute way more pixels, right? So one option could be basically just to check all the pixels, right, to see if they are inside the triangle or not, right? And yeah, this could be a nice idea. We could, for example, see every edge of the triangle as an implicit function, right? So we can check basically if the pixels are either on one side or the other side, right? You could also define normals for these edges from the triangle and basically do exactly the same, computing a dot product, right? So if it's positive or negative, you know if it's outside or inside. The problem is that this is a particularly bad idea if we have something like this, right? You can have a huge image with a lot of pixels and just a very tiny triangle in the middle, right? And this is something that we usually have, right? Not because we have a single triangle in the scene, but because we have a huge model that maybe has millions of polygons or millions of triangles, and those triangles are indeed very small compared with the entire image, right? So checking all the pixels for every triangle when you have probably thousands of triangles, that is basically, yeah, a very bad idea. Another idea that actually you see sometimes in a couple of books is, okay, let's have this option of computing a bounding box, right, for each triangle, and let's only care about the pixels that are inside that bounding box, right? And yes, this could be maybe a good idea. However, this is a bad idea if you have a situation like this, right? A very, very thin triangle, right? And it's also inclined, right, in this case, and basically the bounding box is huge, and you are also like wasting a lot of resources checking pixels are basically not inside the triangle, right? And probably you'll say, hey Enrique, but you told us that we usually, in computer graphics, we usually avoid this type of triangles, right? That we usually have triangles that have like a better shape, and this is a very ugly triangle, right? So why, if we are kind of avoiding those type of triangles, why we can have something like this? Well, remember, this triangle that we are seeing here, it's a 2D version, is a 2D projection of a triangle that is actually in 3D, right? So let's imagine, for example, that this point and this point are basically at the same depth, but this point, this vertex right here, could be way far, right? So maybe this triangle is not actually a thin triangle, but a triangle that has a very nice shape, right? But its projection, because it's basically rotated, its projection is very slim, right? So this actually happens a lot of times, right? So yeah, the bounding box solution is not a good idea. So the solution is an algorithm that is actually quite old. I think it's from the 70s. That is called the scanline fill or scan conversion. Okay, and the way it works is as following. So the first step of this algorithm is to split the polygon or the triangle in horizontal lines, right? So in this case, for example, for this point right here, I'm not creating any splitting, right? Because these are basically the top and bottom corners of my triangle. But for this pixel in particular, sorry, for this vertex in particular, right? So we will draw basically a line, a horizontal line. So this is the first step. And the next step is, or basically when splitting the triangle like this, we get 4 edges that are basically called edge trackers, right? So in this case, we have 4 edge trackers. So each section here is an edge tracker. And we will basically compute the entire algorithm in these 2 chunks, right? And everything can be parallelized and is super efficient. So these edge trackers, what they do is basically we will use the information from these edge trackers. So remember, in the end, we have the X, Y, and Z coordinates, right? From this, from the points from the triangle, right? So for each edge tracker, basically we will have the information from each vertex, right? So we can basically compute the line between those, right? So basically for each edge tracker, we compute its intersection with each row of pixels. And that is actually very cheap, right? So for each edge, we get basically the pixels the pixel that is basically touching that row in particular. And for example, here it seems that I'm missing some pixels, right? But actually I'm not, because in this case we're just like looping for each row, right? So I'm not skipping anything here, because this one, this pixel right here is on this row, and the next row is already filled with this one, right? So it seems that I'm missing information, but I'm not. This is very, very efficient, right, in terms of the amount of information that I need to compute. So I do the same for all 4 edges, and I end up with something like this, right? With this, basically the pixels that are touching the border of the triangle. This is the second step of this scanline conversion algorithm. And the next step is basically we have these pixels, right? And these pixels are basically ordered by the edge trackers, right? So if this was the first edge tracker, so we have 1, 2, 3, 4, 5. So basically the order of these pixels, right, is exactly in the order in which I process them. And again, I mean, here I'm showing you this like in a counterclockwise order, but in fact, this can be computed in parallel, right? So maybe this was the first one and this one the second one, and yeah, so the order can be completely different, right? So the next step, the third step of the algorithm, is basically to order those pixels by scan lines, basically by rows, and also by its increasing x coordinate, right? So in this case, now the order changed, right? So now we have 1, 2, 3, 4, 5, 6, 7. So for each row, right, for each row of pixels, we have these like pairs of intersection, right? The next step, I think it will be very obvious for you at this moment, we just fill the span between pairs of intersections, right? So for each row, we just fill everything that is in between 4 and 5, in between 8 and 9, and in between 14 and 15 and everything, right? And again, this is done in parallel and is super, super cheap, right? So we end up with this, the final result, basically the discrete version of this continuous object that is this triangle. And the beauty of, or one of the beauties of this algorithm is that we can actually do the same for an entire set of triangles, right? So it seems that we need to perform this for single triangles. Well, in fact, after the first version of this algorithm was created, another scientist that I don't remember the name, but I think was also in the 70s, came up with the idea of saying, okay, I think we can do this for an entire mesh, right? So regardless of how a group of triangles is actually triangulated, or a piece of mesh or a polygon is triangulated, regardless of that, you can basically perform exactly the same operation with this algorithm, right? So in this case, for example, this polygon is basically, again, split in these horizontal lines, which basically that is also called trapezoid splitting, right? And we perfectly can do exactly the same, right? So we only compute the sides. So it's really nice because we can, again, we can basically, what computers do in this case, they can process an entire set of, entire piece of mesh, right? And again, it doesn't matter how it's basically triangulated, and you're only computing the intersection between the edges, right? Between basically the borders of that entire polygon, and everything else is just spanning the gaps, or filling the gaps. So that's it. This is how the scanline algorithm works, and it's really nice, right? You can even read about the actual patent. I mean, there are several patents on this algorithm in particular, but this is a interesting one. This is from Sadhna Gupta, and I mean, with other inventors, I don't remember the names. So you can actually read the patent if you want. It's obviously incredibly complicated, and it's quite complicated. But yeah, but you can see a little bit of information about that. So yeah, great. That's it. Well, it turns out that is not exactly the final solution. Okay, there is a problem there. It's a nice algorithm. It's really smart in my own opinion. I think it's a very elegant algorithm. But again, I told you this is from a long time ago. This is probably, yeah, I think it's from the 70s, the original idea, right? So it turns out that this algorithm is very good in general for large triangles, right? For very coarse meshes. And yes, of course, in the 70s, 80s, probably still in the 90s, right? It was not as common to have meshes. At least we are talking about real time rendering, right? Not ray tracing. So in real time rendering, we are talking about video games, right? So video games 10 years ago or 15 years ago, having a million polygons, right? It was just crazy, right? I mean, the hardware was not prepared for that. So yeah, at that time, the type of meshes we were basically rendering in a typical video game, they were basically low poly meshes, low poly models, right? However, in modern days, right, we do have those type of meshes, but very high density meshes, right? So basically, this method is not as relevant anymore, at least with modern GPUs, and it is considered an old school method. However, it's not dead. I mean, it's not relevant anymore, not right now, but it's not dead, and I will talk about it a bit later. But there are still some interesting things about this algorithm. The way you compute the actual coordinates from the portion of the triangle, right, aka the fragment that basically correspond to each pixel. It's called the edge walking algorithm, and it's really nice. You can read about it on this URL. If you find it interesting, I mean, yeah, I mean, maybe we can make an extra video on that. But again, the thing is, computer graphics is so huge that we need probably we could spend years talking about computer graphics, right? I mean, if we spend time on every single algorithm, we will spend a lot of time. But it is something interesting, and I will probably talk a little bit about this particular way of this particular algorithm, the edge walking algorithm, when we talk about ray tracing. But basically, the idea is that when you are computing the actual coordinates from, for example, this fragment here, one way to see this is like, this is like sending a ray, right? Like ray casting, basically like ray tracing, right? This is similar to basically doing ray tracing, sending a ray and basically intersecting that ray with that specific triangle in that specific position and getting the intersection, right? And this is one way in which you can compute the actual coordinates of that, right? There's another way, which is very clever, which is this edge walking algorithm. And again, you can read about it in this URL. This is, I think this is a document from 2004 or something like that, or maybe older, maybe, no, it's maybe older, maybe 1997 or something like that. It's very old. But it talks about this idea. So basically the idea is, instead of computing directly using a raycasting technique, it is by basically computing increments, right? So because at this point your coordinates can be already transformed in the screen coordinates. What I mean with this, I mean that this screen is basically 18 by 18 pixels. So your coordinates could be already transformed in this 18 by 18 scale, right? Which means that this is 1 unit and 1 unit and 1 unit, right? So because your coordinates can be already transformed in this space coordinates, this is screen coordinates, sorry. you can take that as an advantage and basically compute the actual coordinates of the fragments by computing just an increment, right? Is basically, imagine that, for example, I have the coordinates of this point right here. So in order to compute the next point, right, instead of just sending a ray trace, right, or casting a ray, I just compute an increment value, right, for x and y coordinates, and also to the z coordinate, because at this point you still have depth information, right? And basically just computing an increment factor, you can basically compute the actual correct coordinate for x, y, and z. And then for the next one, it's the same. Just use the same increment and compute the next one, the next one, the next one. So it's a very nice algorithm. It's called the edge walking algorithm. And again, you can read about it on this tiny URL. So that's the thing, right? This is, again, not as relevant anymore. So what do you do with a more modern solution, right? And I will not say a smarter solution, because, yeah, I mean, the scan line algorithm, it is very smart. So what do we do? Well, it turns out that for modern GPUs, and because the way those GPUs are designed electronically, I mean, like how the hardware is designed, modern GPUs actually use edge equations, right? And so those that we said at the very beginning that they will be incredibly expensive, right? Saying like, yeah, computing basically all the pixels from the image, right? Every single pixel, and checking with the edge equations from the triangle if they're inside outside, right? We said no, that is super expensive, right? You're just testing for too many pixels, right, on an image, right? Well, it turns out that modern GPUs use that, at least this year to 2020, right? And the way you do it is by first basically split the problem or parallelize the problem by rasterizing a coarse resolution first. So yeah, it's true. If you compute every single pixel in the original image, it will be a waste of time. But now we can actually parallelize and create like blocks or chunks. Create blocks of pixels, right? So in this case, for example, I could have blocks of 6 by 6, right? In this case, because this is 18 by 18. So in this case, for example, 6 by 6. And this will be incredibly cheap, right? Incredibly easy to parallelize in modern GPUs, and incredibly cheap to basically compute an image. This is like rasterizing an image that is basically 3 by 3 pixels, right? It's super cheap. So basically, after you do this, you basically pixelate that or rasterize that, and you can discard the pixels or the area or the groups or the blocks of pixels that are basically not relevant anymore, and you just continue incrementing the resolution from the sections that basically survived. So now you can, for example, compute now with blocks of 3 by 3, and you discard the areas that you don't need, right? And you end up with something like this, right? With basically the final result. And so this is what we use in modern GPUs. And however, again, I want you to tell you something that I think is in general valid for computer science in general, but in particular in computer graphics. Algorithms just evolve, right? And this depends on hardware or trends or other factors. And so, and this is probably only my opinion, but I think there is no such thing as a dead algorithm. Because, for example, this algorithm of just checking a pixel using edge equations, it was considered dead in somehow, right? When someone came up with the scanline algorithm, right? But it turns out that we basically bring that idea back, because now with modern hardware, that one is easier, right? Well, it could be the same for a scanline algorithm, right? Right now, it is considered not as relevant anymore, but it doesn't mean that we will never use it again. So everything can come back. So I think, again, this is only my opinion, but I think unless we are talking about a very, very dumb algorithm, right? If someone tells you, oh, we will never use that algorithm again, it's probably wrong, right? And also in particular in computer graphics, I think it's very relevant to keep learning not only the most modern trends and things that, right? I mean, you should be reading right now papers from SIGGRAPH and papers from CVPR, and there are just impressive new stuff out there, right? I mean, deep learning is causing probably a revolution in generally in rendering, and some people believe that deep learning might affect a lot of the ray tracing algorithms in general, or like in general this type of algorithms. And I also think that is probably true. I think modern computer graphics, maybe in two or 3 years from now, will be using a lot of deep learning already in commercial things. I mean, we are already using deep learning in a lot of things. But again, what I mean is, maybe in the future we also will use a different hardware, right? And there's this trend of internet of things. So we're already like connecting different devices, not just your computer, but different devices to the internet and getting data from a lot of places. And we will probably start using graphic devices on different objects rather than just your computer or your cell phone, right? So eventually, maybe we will have like tiny graphics devices in the back of a bottle or in the very tiny medical device or something like that. And so these devices, for example, they might need sophisticated graphics, right, or sophisticated visualizations for depending of what the user might need at that time. And those type of devices will probably not have the largest and most sophisticated GPU, right? Because GPUs are also like super expensive and super sophisticated, right? So again, different hardware needs different algorithms, right? So it is important for you to, again, not only learn the most modern version of computer graphics, but also once in a while go back and see, okay, how people were solving problems in the 60s, in the 70s, because we will probably start to get those ideas back once we start using graphics hardware, right? That is basically like very basic version of graphics. And again, yeah, I mean, this is only my opinion, but so yeah, this was basically the topic of rasterization. So the next in the next lecture we will talk about how having this rasterization already done, having this set of pixels that basically correspond to a specific fragment, right? How we actually compute the interpolated values, right? And we will use barycentric coordinates. So that will be our next step, and I hope you like this video. Thanks, everybody.